All right, so let us start our first lecture. So all of you can access to Canvas, right? So this lecture now will be on Canvas. And also I'm gonna put the videos on Canvas so that you can review everything that you have. So again, in the first lecture we're gonna review about some of the knowledge from linear algebra. All right, so first 1.1, linear algebra. So suppose that you have two vectors. Suppose that we have two vectors. Two vectors. The first one is 1, 2, and the second one is 3, 4. All right? So what is the inner product of these two vectors? So here I have the first vector, which is 0, 1, 2, 1, 2, 3, and this is 4. So the first one is 1, 2, right? This is A. And the second one is 3, 4. This is the second vector, right? So the first vector is the vector 1, 2. So 1, 2 are the coordinates of A. The second vector B is the vector 3, 4, and 3, 4 are the coordinates of B, right? So the inner product of A and B. So who remember what is the inner product of A and B?
The dot product?
Yes?
The dot product?
Yes. So the dot product, right? So what is the dot product of A and B? So how do you compute the dot product of A and B?
Summation
Yes?
of multiplying each vector.
Excellent. Can you sign at the back of the paper, please? And so you sign at the back here, and you check the attendance, and you show it to your friends and sign it. Thank you. So, so every time you answer a good, so every time you sign at the back of the paper, you got 1 extra point for the next homework. So the maximum, the scores for the homework is 15. But if you have 1 good answer, you can add 1 extra point there. So you're gonna have 16, right? So the dot product of the two vector A and B will be computed by multiplying the coordinates, and you take a sum. So here you have 1 times 3 plus 2 times 4, and this is 3 plus A. This gives you 11. All right. So you multiply all of the coordinates, and you take the sum of all of them. All right. So now suppose that A has B component. B will be B1, B2, BD. So what is the dot product of A and B?
A1, B1 plus A2, B2 plus down to AD, BD.
Excellent. Can you say at the back of the paper, please? So you have A1, B1 plus A2, B2 plus AD, BD. All right? So the dot product is the most important thing in linear algebra. You multiply two vectors by multiplying all of the coordinates, you take a sum. right? So what is the name for D? What is D? What is the quantity D? What is the name for D?
D is like the number of
The number of coordinates. But what is the fancy name for that?
Dimensions.
Dimension. Who said that?
Index. Is what we call it.
Who said dimension? You said yes. Can you sign the back of the paper, please? So D will be dimension
That's not fine.
of the vector. All right. So this D will be the dimension of the vectors. In this case, we are in 2 dimensions. All right. So if A has 2 coordinates, 1 and 2, and B has 2 coordinates, 3 and 4. So this vector is in 2 dimensions. Now suppose that A has D coordinates, A1, A2, AD. So D will be the dimension of the vector A. All right. So you multiply 2 vectors A and B by multiplying all of the coordinates, and you take the sum. It's clear? Questions? Right. So so there's also a very important formula. So if I denote theta to be the angle between A and B, right? So theta is the angle between A and B. I can compute the cosinus of theta. So what is the cosinus of theta? Yes?
magnitude. Oh,
All right, so, yes?
The dot product divided by the product of the magnitudes.
Excellent. Can you say at the back of the paper, please? So the cosinus of theta will be A times B. So you take the dot product and you divide by the length of the vector A times the length of the vector B. Right? So the length of A will be the square root of the square of all of the coordinates. AD square, and the magnitude of A will be B1 square plus B2 square plus BD square. Right? So the length will be this, the length of this segment. All right? So I explain again. So after you understand the dot product of 2 vectors, which is simply multiplying all of the coordinates and take the sum, the next concept will be the angle between the 2 vectors. So I call theta to be the angle between the vector A and the vector B. So cosinus of theta will be the ratio between the dot product of A and B dividing by the product of the length of A and the length of B, right? So this is the length of A. So the length of A will be the square root of A1 square plus A2 square plus AD square, and the length of B will be the square root of B1 square plus the square root of B2 square plus the square root of BD square. It's clear? Questions? So now, remark. So what happened? When theta is 90 degrees. All right? So you can write theta to be 90 degrees or theta to be pi over 2. They are equivalent. Right? So when theta is 90 degrees or theta is pi over 2, they are equivalent, right? So what is the inner product of the 2 vectors?
0.
0. Who said yes, 0? Can you sign at the back of the paper, please? So cosinus of theta will be 0, which means that A dot B divided by A times B is 0, which means that A dot B is 0, right? So which means that if the two vectors are orthogonal, if the two vectors are orthogonal, the dot product, inner product, is 0. All right? Questions? So again, I explain. So from this explanation, what you have is that the cosinus of the angle between the two vectors A and B can be computed as the inner product of A and B dividing by the product of the lengths of A and B, right? Now, suppose that this angle is 90 degrees or pi over 2. The cosinus will be 0. Because the cosinus is 0, the inner product of A and B dividing by the length, the product of the length is 0, which means that the inner product will be 0, right? So in other words, if the two vectors are orthogonal, or the angle between them is pi over 2, then the dot product will be 0. It's clear? Questions? All right, so now let us go to the next one, which is basis. Orthogonal basis. All right, so let us consider the vector A, which is 1, 2. All right. So this is the vector that we considered before. The vector is 1, 2, right? Now I can write this vector under the following form. I have 1, 0, plus 0, 2, right? So 1, 2 can be decomposed as 1, 0, plus 0, 2, right? So this is 1 times 1, 0, plus 2 times 0, 1. All right? So here I have a vector E1. Here I have a vector E2. So E1 will be 1, 0, and E2 will be 0, 1. All right? So A will be 1 times E1 plus 2 times E2. Right? So I explain again. Let us consider the simple example in which the vector A is 1, 2. So this vector A has two coordinates, 1 and 2. So I can decompose this vector under the form. So 1, 2 will be 1, 0 plus 0, 2. All right? So 1, 0 will be 1 times 1, 0, and 0, 2 will be 2 times 0, 1. I call E1 to be 0, 1, and E2 to be 0, E1 to be 1, 0, and E2 to be 0, 1. Right? So I can write A to be 1 times E1 plus 2 times E2. So what can you say about E1 and E2?
They were orthogonal, because it'll be 90 degrees.
Yes, excellent. Who said that? Yes, can you sign in the back of the paper, please? So if you multiply E1 and E2, what you get is the following. You have 1 times 0 times 0, 1. And this gives you 1 times 0 plus 0 times 1, and this is 0. Right? So E1 and E2 are orthogonal. All right? Which means that so now let me explain this again. After I decompose A into 1 times E1 plus 2 times E2, right? I observe that E1 times E2 will give you 1, 0 times 0, 1, and this is 1 times 0 plus 0 times 1, and this is 0. Because the inner product of E1 and E2 is 0, I can say that E1 and E2, they are orthogonal. So in this case, E1, E2 form an orthogonal basis. Right? And A can be expressed as a linear combination of E1, E2. Right? So A in this case will be E1 plus 2 E2. So I explain again. In this case, because E1 and E2, the inner product of E1 and E2 is 0, we can say that E1 and E2 are orthogonal, right? So in this case, we say that the two vectors E1 and E2 forms an orthogonal basis. So this is the notation of a set. So this is a set that contains two vectors E1 and E2, right? So the set E1, E2 forms an orthogonal basis, and the vector A can be expressed as a linear combination of the two vectors E1 and E2. So in this case, A is E1 plus 2 E2, right? It's clear? Questions? In general, so in this case, the dimension, is 2, right? So in this case, the dimension is 2, and we say that A belongs to R2, right? So this is another notation that we need to recall, because here you have, so the vector A has two components, right? Well, 1 and 2. So we say that the dimension is 2, and A belongs to R2. Is it clear? Questions? Now, so in general, so let E1, ED be an orthogonal basis in RD. All right? Any vector V in RD can be written as V is V1 times E1 plus V2 times E2 times VD times ED, right? So in general, in D dimension, if you have a vector V, then this vector V can be decomposed in terms of this orthogonal basis. It's clear? Questions? So example, so let us try to understand the case when 3. All right, so you have V will be 1, 2, 3. Clear? So I can decompose V as 1, 0, 0 plus 0, 2, 0, 0, 0, 3. All right? And this is 1 times 1, 0, 0 plus 2 times 0, 1, 0 plus 3 times 0, 0, 1. So this one will be E1, this one will be E2, and this one will be E3. So I'm gonna have E1, E2, E3. So this gonna give you E1 plus 2 E2 plus 3 E3. All right? So I explain again. In D dimension, any vector, so suppose that you give me an orthogonal basis, I can decompose any vector in RD as a linear combination of all of those bases, right? So V can be written like V times E1 plus V2 times E2 plus VD times ED. Example. So in the previous case, the dimension is 2. So now let us consider 3 dimension. So in 3 dimension, the vector that I choose is 1, 2, 3. So I can decompose. So this is 1, 0, 0 plus 0, 2, 0 plus 0, 0, 3. And this can be written like 1 times E1 plus 2 times E2 plus 3 times E3, right? In which E1 will be 1, 0, 0, E2 will be 0, 1, 0, E3 will be 0, 0, 1, right? So then I can write this like E1 plus 2E2 plus 3 E3. So now I'm gonna check if they are orthogonal, right? But they will be orthogonal, right? Because E1 times E2 will be 0 times 1, 0, 0 times 0, 1, 0, and this is 1 times 0 plus 0 times 1 plus 0 times 0, and this is 0. All right, and so I explain again. So after I decompose V, like 1, 2, 3, this is the vector V. I can decompose this like 1 times 1, 0, 0, which is E1, plus 2, 0, 1, 0, which is E2, and the next one is 3, 0, 0, 1, which is E3, right? I'm gonna check if they are orthogonal. So I multiply E1 and E2, so I'm gonna get 0, 1, 0, 0 times 0, 1, 0, that gives me 0, all right? Which means that they are orthogonal. Similarly, we also have E2 times E3 is 0, and E3 times E1 is 0, right? So in this case, we say that since E1 is orthogonal with E2, so this notation means that orthogonal. E2 is orthogonal to E3, and E1 is orthogonal to E3. So they are orthogonal. All right? Is it clear? So I explain again. In this, so in RD, you have an orthogonal basis in the sense that all of them are orthogonal to each other. Then you can write a vector V as a linear combination on the basis. All right? So in this case, E1 will be 0, 1, 0. E2 will be 0. E1 will be 1, 0, 0. E2 will be 0, 1, 0. And E3 will be 0, 0, 1. So if you multiply all of these E, you're going to have E1 times E2 will be 0. You can check that E2 times E3 is also 0, and E3 times E1 is also 0. Then I say that E1 is orthogonal to E2. So this is the notation for orthogonal. So this is orthogonal. And then you also have E2 is orthogonal to E3 and E1 is orthogonal to E3. So this basis has all of the components being orthogonal, right? Questions? It's clear? Right. So let us try to compute all of those. So basically, this is the formula that we have. We have V is V1 times E1 plus V2 times E2 plus VD times ED, right? So given V, E1, ED, how can we compute V1, VD? Now, in D dimension, I have a vector V, right? And I have an orthogonal basis, E1 to ED. I can decompose V as the sum of V1, E1 plus V2, E2 plus VD, ED, right? Important remark is that V1, VD, they are numbers. And V, E1, ED, they are vectors. All right? We know that we can decompose V under this form, in which V1, V2, VD, they are the numbers associated to all of those components of the orthogonal basis. Now, the question is, how can you compute V1, V2, VD if I give you in advance the vector V and the basis E1 to ED?
If you only have the one vector, then you'd be able to just take the value for each axis and have that be the V1, V2, and on, because the orthogonal basis would be one, would just be the unit vector for each axis.
This is a good remark. Can you sign the back of the paper, please?
Well,
But what if I have a basis which is 1, 2, 3 and not 1, 0, 0, 0? Right. So how can you compare V1, V2, VD? So there's a very, can you sign it? And so now the idea of this is the following, right? So suppose that I multiply V with E1. What do I get? Now I'm gonna multiply V with E1, have V1, E1 plus V2, E2 plus VD, ED times E1, right? Now I multiply the vector V with E1. So, which means that I have to have V1, E1 plus V2, E2 plus VD, ED, right? Now this gives me V1 times E1, E1. I'm going to multiply this inside, right? So I'm going to have V1, E1, E1. I don't need this parenthesis. So I have V2, E2, E1 plus VD, ED, E1. So now what happens?
All of the, everything following that first entry cancels out because all of these are orthogonal, except for E1 and E1.
Yes, can you sign it at the back of the paper, please? Right, so now you see that this is 0, this is 0, and this is not 0, right? So why? So because E1, E2, E3, ED is an orthogonal basis. Right? which means that you have what? You have E2 is orthogonal to E1, which means that E2 times E1 is 0. And you have E3 is orthogonal to E1, which means that E3 times E1 is 0. Alright? And then everything will be 0. ED is orthogonal to E1, so then you're going to have ED times E1 is 0. Alright? So I explain again. Suppose that I have this decomposition. V is V1 times E1 plus V2 times E2 plus V3 times E3 plus VD times ED. Right? Now what I do is I multiply V with E1. When I multiply V with E1, I have V1 E1 plus V2 E2 plus VD ED times E1. Alright? So when I multiply everything with E1, I can distribute E1 inside the sum. I'm going to have V1 E1 times E1, V2 times E2, V2 times E2 times E1 plus VD times ED times E1. Alright? This is an orthogonal basis, meaning that E2 has to be orthogonal to E1. So in other words, E2 times E1 is 0, so I put it here. Alright? Then ED times has to be orthogonal to E1, which means that ED times E1 has to be 0, and then put it here. Alright? So all of the terms here are 0, except the first term. Right? So why is it not 0?
It's multiplying by itself.
Right. So this is an inner product where you multiply a vector with this cell and this is not 0. Can you say the back? Please. So, alright, so what is E1 times E1? I want an explicit value for E1 times E1.
1.
This is not really 1 because this is not, the length of E1 is not 1. Right? So what is it?
It's the square of the length of the E1.
Excellent. Okay. Can you sign at the back of the paper, please? So you have E1 times E1 times cosinus of theta. So theta here will be 0 because you have the same vector, right? So angle between the vector and itself is 0. So this should be 0. And this gives me, so this is 1, so this is E1 squared. Alright? So now what you have is that, okay, V times E1 will be V1 times E1 times E1. Right? So because the leftover is 0. And this gives me V1 times E1 squared. So V1 should be V times E1 divided by E1 squared. Or this is also V times E1 divided by E1 times E1. It's good, yes?
Is E the identity? Like the identity element?
No, no. So E can be anything, right? So very good questions, right? So I can choose. So I can choose E1. So suppose that, okay, example. Suppose that D is 2, right? I can choose E1 to be 1, 2, and E2 to be minus 2, 1, right? And then what is the inner product? So you have E1 times E2 will be 1 times minus 2 plus 2 times 1. This is minus 2 plus 2, and this is 0. All right? So the E1 and E2 are also orthogonal in dimension 2, right? So which means that E1 and E2 is also an orthogonal basis. In R2. Alright? In other words, you can have many orthogonal bases. There are infinite orthogonal bases, right? Example, in dimension 2, I choose two vectors. The first one is 1, 2. The second one is minus 2, 1. I multiply them. I have 1 times minus 2 plus 2 times 1. This gives me 2 plus 2 is 0. All right? These two vectors are orthogonal in R2. And they form an orthogonal basis, right? So you know that in the previous one, in the previous example, you have what? You have 1, 0, 0, 1. This is orthogonal basis for R2. Right? So this is what we see in the previous example. 1, 0 and 0, 1 is an orthogonal basis for R2. But this is also another basis. Right? So you can have multiple bases, and everything will change. Everything will change when you change the basis. It's also an orthogonal basis for R2. All right? Questions? It's clear? Right. So you understand this, how to compute V1, right? So now we're gonna try, so this is an example answering your questions, saying that you have many orthogonal bases for R2, R3, R4, etc. Right? As long as they're orthogonal, you have an orthogonal basis. But in R2, you have only 2 vectors. In R3, you have 3 vectors, right? In R3, if you can find 3 vectors who are orthogonal, then this is an orthogonal basis for R3. Right? So in RD, if we can find D vectors E1, ED, such that they are orthogonal, then this is an orthogonal basis. Is an orthogonal basis. Right? So in R2, I found this guy. They are orthogonal. There are 2 vectors, so this is an orthogonal basis. In RD, I can find D vectors such that they're all orthogonals. So then I say that this is also an orthogonal basis. It's clear? Now coming back to this business. So the key idea is that you multiply everything with E1. All of the terms that contains E2, ED cancel out. And what you have is V times E1 is V1 times E1 times E1. So E1 times E1 can be computed using the formula that we had before. So you have E1, the length of E1, times the length of E1, times the cosinus between the angle between E1 and E1. But the angle between one vector and itself is 0. So this should be 1. So E1 times E1 should be E1 squared. So then I'm going to have V1, E1 squared is V times E1. So which means that V1 is V times E1 dividing by E1 squared, and this is V times E1 dividing by E1 times E1. Right? Questions? It's clear? You can repeat this to the other vectors as well. So let me try to do that with E2. So now I have V, which is V1 times E1 plus VD times ED. All right? And I want to compute V2. So how do I compute V2? Excellent. Can you say it at the back of the paper, please? So now I'm going to multiply this with E2. Right? And this gives me V1 times E1 plus V2 times E2 plus VD times ED. Now you multiply with E2. All right? So what you get is V1, E1 times E2 plus V2 times E2 times E2 plus VD times ED times E2. All right? So I'm going to apply the same trick. I'm going to multiply V with E2. I'm going to get V1 E1 plus V2 E2 plus VD ET times E2. Right? So I'm going to distribute this inside the sum. I'm going to have E1 E1, E1 E2, E2 E2, ED E2. Right? So this is going to be 0. This is going to be different from 0. And this is going to be 0. All right? So everything will be 0 except E2 E2. Right? Now I have V times E2 is equal to V2 E2 times E2. All right? So V2 will be V times E2 divided by E2 times E2. And again, you can use the formula in the previous one, and you have this one. So this is the formula that you have. All right, so I repeat. You express V in this form. What you do is you multiply everything with E2, right? So if you want to find V2, you have to multiply with E2. If you want to find V3, you have to multiply V with E3. So when you multiply this, all of the terms that do not contain E2, E2 will be 0. So the leftover is V times E2 is V2, E2, E2. So V2 will be V times E2 divided by E2, E2. And this is the formula for V2. So in general, the general formula is the following. General formula will be the following. So you have V1 will be V times E1 divided by E1, E1. V times E1 divided by E1 squared. V2 will be V times E2 divided by E2 E2. And this gives you V times E2 divided by E2 squared. V3 will be V times E3 divided by E3, E3. All right, and this gives you V times E3 divided by E3 squared, etc. And you have VD will be V times ED divided by ED. And this gives you V times ED divided by ED squared. All right? And the formula for V is V1, E1 plus VD, ED. All right? Questions? So I explain again. So you give me a vector V and an orthogonal basis E1 to ED, right? I can decompose V in terms of E1 to ED. So V will be V1 times E1 plus VD times ED, right? So the formula for V1, V2, VD will be the following. V1 will be V times E1 divided by E1, E1. V2 will be V times E2 divided by E2, E2. And VD will be V times ED divided by ED, ED. It's good? It's clear? Questions? So this formula is very important because we're going to use that for Fourier series. All right? Now, let us go to one example, which is an example that we have in the lecture notes as well. So this is example 1.1.4 in the lecture note. 1.1.4. So in this case, we are in 3 dimensions. I consider E1, which is 1, 2, 1. 1, 2, 1. Dimension is 3. Alright. The second one is 1 minus 1, 1. 1 minus 1, 1. And the next one is 0, 1 minus 1. 0, 1 minus 1. 1, 0. This is 1, 2, 1, 1 minus 1, 1. 1, 0 minus 1. Alright? So, in this case, we have three vectors. 1, 2, 1, 1 minus 1, 1, and 1, 0 minus 1. Alright? So, so we're gonna do is that, check that E1, E2, E3, and orthogonal. So the first step we want to do is to check that these three vectors are orthogonal. So if they are orthogonal, we have three vectors that are orthogonal in dimension 3, which means that these form an orthogonal basis, right? It's clear? Now, let us multiply E1 and E2. So E1 and E2 will be 1, 2, 1 times 1 minus 1, 1. And this is 1 times 1 plus 2 times minus 1 plus 1 times 1. Alright, and this gives me 1 minus 2 plus 1, and this is 0. Right? So in this case, I have E1 and E2 are orthogonal. Right? I explain again. I give you three vectors. I claim that we have to check that they are orthogonal because we have three vectors that are orthogonal in dimension 3, because here you have three components, right? So you have three coordinates, which means that this is in dimension 3. So you have three vectors that are orthogonal in dimension 3. This will be an orthogonal basis for dimension 3. So I have 1. So first I'm going to check E1 times E2. I have 1, 2, 1 times 1 minus 1, 1. So this is 1, 1 plus 2 minus 1 plus 1 times 1, and this is 0, which means that E1 is orthogonal to E2. Now I have E1 times E3. So I have 1, 2, 1 times 1, 0 minus 1. Alright? This is 1 times 1 plus 2 times 0 plus 1 times minus 1. 1 times 1. So I have 1 plus 0 minus 1, and this is 0. So which means that E1 is orthogonal to E3. Right? So first I check that E1 and E2 are orthogonal. This is standard because you have to multiply all of the coordinates and you take the sum, and this is 0. For the second one, you also do the same. You have 1, 2, 1 times 1, 0 minus 1, and you get 0, which means that the first one and the third one are orthogonal, right? And so the next one will be E2 times E3 will be 1 minus 1, 1, 1, 0 minus 1. So this gives me 1 times 1 plus minus 1 times 0 minus 1 times 1 plus 1 minus 1, and this is also 0, which means that E2 is orthogonal to E3. Alright? So the last thing you have to check is E2 times E3. So you have E2 times E3 is 1 minus 1, 1 times 1, 0 minus 1. This also gives you 0. Alright? So which means that E2 is also orthogonal to E3. So finally, E1, E2, E3 are orthogonal. So we have three vectors, right? We have three vectors, three orthogonal vectors in dimension 3. So E1, E2, E3 forms an orthogonal basis. All right? It's clear? So in this case, you have three vectors orthogonal in dimension 3. So this is an orthogonal basis. So what happened in dimension 4? How many vectors do I need? 4, right? So in dimension D, you need D vectors that are orthogonal to have an orthogonal basis. And you can have many of them, right? So this is an orthogonal basis. Now, the next step is that, okay, I have this vector V, which is 3, 5, 7. Now I have this vector V, which is 3, 5, 7. 3, 5, 7. All right? So I have to express V in terms of E1, E2, E3. So express V as V is V1 times E1 plus V2 times E2 plus V3 times E3. All right? So now I give you a vector 3, 5, 7. I have to write V as a linear combination of the basis. So I have V is V1 times E1 plus V2 times E2 plus V3 times E3, right? So how do I compute V1?
Multiplied by E.
Yes. Can you sign at the back of the paper, please? So what I have is that V1 will be V multiplied with E1, right? Dividing by E1 times E1. All right? So I compute V1 using the formula that we have before. So I have V1 is V times E1 dividing by E1 times E1. So what I have is 3, 5, 7 times 1, 2, 1. And I divide by 1, 2, 1 times 1, 2, 1. All right? So this is the formula that we have. V1 is V times E1 dividing by E1 times E1. So this is 3, 5, 7 times 1, 2, 1 dividing by 1, 2, 1 times 1, 2, 1. So let us compute this. So this is 3 plus 10 plus 7 dividing by 1 plus 4 plus 1. And this gives me 20 over 6. And this is 10 over 3. All right? Now explain again. To compute V1, I'm going to use the formula before. I have V1 is E1 times V1, V dividing by E1 times E1. So V times E will be 3, 5, 7 times 1, 2, 1. E1 times E1 will be 1, 2, 1 times 1, 2, 1. And this gives me 10 over 3. It's clear? Now, let us compute V2. So V2 will be V times E2 dividing by E2 times E2. And this is what? This is 3, 5, 7 times 1 minus 1, 1 divided by 1 minus 1, 1, 1 minus 1, 1. Right, so this is 3 minus 5 plus 7 dividing by 1 plus 1 plus 1. And this is 5 over 3. All right? Now, I explain again. So how do we compute V2? We compute V2 by multiplying V with E2 and dividing by the inner product of E2 and T2. So I do the computation, I get 5 over 3, right? Now, what is V3? V3 will be V times E3 dividing by E3 times E3. So this gives me 575 times 1, 0 minus 1 dividing by 1, 0 minus 1 times 1, 0 minus 1. So this gives me 3 plus 0 minus 7 over 1 plus 0 plus 1, and this is minus 1, minus 2. All right? So V3 can be computed similarly. I only have V3 is V times E3 dividing by E3 times E3. So I multiply 357 with 0 minus 1 and divide and multiply 1, 0 minus 1 with 1, 0 minus 1. So the first one gives me 3 plus 0 minus 7. The second one gives me 1, 0, 1. So this is minus 2. All right? So final answer is the following. So I can write V like 10 over 3 E1 plus 5 over 3 E2 plus minus 2 E3, right? So now you put everything into the formula here. I'm going to replace V1 with 10 over 3. I'm going to replace V2 with 5 over 3. And I'm going to replace V3 with minus 2. So basically, this is the formula that I have. To be more explicit, we have the following. So we have 375 is 10 over 3 of 1, 2, 1 plus 5 over 3 1 minus 1, 1 plus minus 2 of 1, 0 minus 1. Right, so this is the formula that we have. All right? So, right? So basically, what I do from here to here is to replace V by 357. So I have 357 is 10 over 3 of E1, which is this one, plus 5 over 3 of E2, which is this one, and minus 2 of E3, which is this one, right? Yes?
So now E1, E2, E3 can be any orthogonal basis, right? It doesn't
Yes.
they don't have to be that exact three. So now that we've solved for V1, V2, V3, that can be 1, 0, 0, 0, 1, 0.
No, you cannot replace E1 by anything else.
Those have to be those ones?
Yes, E1 has to be this one. So if you want to replace that by 1, 0, 0, you have to use the same formula. You have to compute again V1, V2, V3. So this constant, 10 over 3, 5 over 3, minus 2, have to be for this basis.
Okay.
So for each basis, you have a new set of constant, right? Clear? All right, so we still have 2 minutes, right?
Sorry.
No. Right, I just want to check. So we have still have 2 minutes, right? Right. So what we have learned so far is the following things, which is the most important thing of this lecture. All right. In ADI, you have an orthogonal basis, and you can express a vector V in terms of V1, E1 plus VD, ED. All right. So this is what happened in ADI in D dimension. So there are cases in which the dimension is infinite, right? So how can we extend this to the function space, right? So for instance, if I have a function, if we have a function space V, which is not AD, which is not D dimension, but infinite dimension, can we find a a basis. Phi1, Phi2, right? Such that we can express a function f, any function f, under the form f is f1 times e1 phi1 plus f2 times phi2 plus etc. Right? So the next class, in the next class, we're gonna try to extend this concept to function spaces. In function spaces, the dimension is infinite. So you have to have a new way of defining the basis so that you can express any function in terms of the basis. All right? So see you on Thursday.